Hi everyone. So in this series, we'll be looking at matrices, and be looking at the different components of matrices, starting with addition, transpose, multiplication, determinant, inverse, and so on. So we'll be doing this in series form. So like for example, in this video, we want to look at maybe 3 or 4 subheadings. Then the series will just continue just like that. So in case you have a question relating to what we'll be doing, please feel free to drop it in the comments. Alternatively, if you have a question on matrices away from these subtopics we've chosen, because I'm aware that there are things that we didn't include, so you can feel free to ask a question, pose a question, or request for a video. We can do that for you. So let's go ahead and start. So we'll be starting with addition and subtraction of matrices. Let's jump straight into it. Okay, so let's see how we can add and subtract matrices. So to start with, it's important to note that there's one condition that must be followed. Matrices can only be added and subtracted if they have the same order. Now, what is an order? When we say same order, what does this mean? So, order of a matrix simply talks about how many rows and columns a particular matrix has. For example, if I have this matrix, A, B, C, D, E, F, this matrix has 3 rows and 2 columns. So the order of this matrix is a 3 by 2. So order of a matrix simply means how many rows against columns does the matrix have. So for example, this matrix that I have here, it's a 2 by 2. It has 2 rows, 2 columns. The matrix that I have here, it's a 3 by 2, just like this one. It has 3 rows and 2 columns. So order of a matrix simply means the number of rows and the number of columns. That's the order of a matrix. So let's see how we can add these two matrices here. Remember, the condition is that the order must be the same. So if the order is not the same, the matrices cannot be added or subtracted. If the order is the same and two matrices are being added, you just add the corresponding values on each particular position. So in this case, we'll simply say 4 plus 4, since we're adding. So, sorry, 4 plus 2, of which we get a 6. 0 plus negative 5, we'll get a minus 5. And negative 1 plus negative 1, we'll get a minus 2. Then 3 plus negative 4, we'll get a minus 1. As simple as that. Meaning that even the answer, of course, will be in the same order as the two matrices were. Next question we have is this one. Let's subtract the two. So are the two orders the same? Yes, they're the same. Are the two matrices having the same order? Yes, they do. So let's do the subtraction. So subtract the corresponding values. It's as easy as that. So 2 minus 5, we'll get a minus 3. 3 minus 3, we get a 0 here. 4 minus negative 1, we'll get a positive 5. 7 minus 2, positive 5. 1 minus 4, minus 3. And negative 3 minus 5, we get a minus 8. Simple as that. So this is how we add and subtract matrices. Now, there's something that I would like to show you where they add a constant to a matrix, then you're supposed to add it to something. So let me just show you another set of examples in which our matrices can be added and subtracted. Here we go. So in this one, the idea is just the same thing. You have two matrices, matrix A and B. They have the same order, and they are being subtracted and added. So let's see how we can go about this. So for the first one, we're subtracting them. So let's just write them down as they are. So matrix A is 2, 1, 6 minus 3. We're subtracting B, which is 5, 0, minus 7. Here we have a 4. So subtracting these two, what do we get? So 2 minus 5, we have minus 3. 6 minus negative 7, we'll have a positive 13. 1 minus 0 is 1. Negative 3 minus 4, we have minus 7. Like that. Let's do the opposite. So we'll start with B. B is 5, 0, minus 7. Here we have a 4. We subtract A, which is 2, 1, 6 minus 3. So corresponding values, 5 minus 2, we have a positive 3. 7 minus negative 7 minus 6, we have minus 13. 0 minus 1, we'll have minus 1. So 4 minus negative 3, we'll have positive 7. So it's just the same thing, though the sign just changes because it's the opposite. Okay. What if matrix A is multiplied with a scalar or what's this? A constant. So what this means is that you have to multiply every element in matrix A with a 2, then you subtract B from that particular result that you get. So multiplying every element in matrix A with a 2, what do we get? We'll have 4, 2, 12, minus 6. So this is 2A. Multiplying everything in there by 2, then we subtract B. B again is 5, 0, minus 7. Here we have a 4. So let's do the subtraction. So 4 minus 5, minus 1, 2 minus 0, 2, 12 minus negative 7, we'll have a positive 19, like that. Then negative 6 minus 4, we'll have a minus 10. Okay. Same thing here. Multiply, or rather, we can say divide every element in matrix A by 2, or multiply everything in matrix A by half. So let's multiply by half. So 2 by half is 1, 6 by half is 3, 1 by half is half, and minus 3 by half is 3 over 2. So this is our matrix A. We are adding matrix B, which is 5, 0, minus 7, 4. What do we get? So 1 plus 5, we get a 6, negative 7 plus 3, we get a minus 4. Half plus 0, we get a half, and negative 1.5 plus 4, we get 5 over 2, or 2.5. Okay, let's quickly do the last question. So in negative B, so everything in B will be multiplied with a negative. So we'll have minus 5, 0, 7, minus 4. Then we add it to 3A. So everything in A will be multiplied with a 3. So what do we get? We'll have 6, 18, 3, minus 9. Now let's add these two. So negative 5 plus 6, we get a 1. 7 plus 18 should get something like 25. 0 plus 3. Then we have negative 4 plus negative 9, we have minus 13. There we have it. Very straightforward. So this is how we add and subtract matrices. As long as the order is the same, you can just go ahead and do it direct with regards to the corresponding values. So let's see how we can find a transpose of a matrix. So let's look at transpose matrices. How do we transpose a matrix? Given a matrix, we have to know how to transpose. So in transpose matrix, the columns, of course, become the rows, and the rows become the columns. What we're talking about is this. If we have been given a matrix, 2, negative 1, 3, and maybe 4, this is our matrix. So if this is our matrix A, then A transpose, so the rows become the columns. So if this is a 2 by 2, it will be difficult to see it on this one, but I'll show you in the next one. So what are the rows? The rows are these horizontal lines that we have, or the numbers in the horizontal line. So that is 2 and 1, the first row. The second row is 3 and 4. So this row, 2 and negative 1, becomes a column here. This row, 3 and 4, becomes a column here. This means we have transposed. So this is A transpose. Let's look at another matrix X. So matrix X, let's say we have 3, negatives, oh sorry, not negative 0, let's say negative 9. Then we'll have 0, that is 4, 2, then 1. That's a random matrix. Now let's find the transpose of this matrix. So this is a 9. This matrix, how many columns does it have? How many rows does it have? The number of rows, we have 2 rows, and it has 3 columns, meaning that its transpose, the rows become the columns. Its transpose must be a 3 by 2, because the rows become the columns become the rows. So to transpose this now, we're going to say the columns are 2 and 3. So the first column is 2 and 3. So this first column becomes the first row, which is 3. I don't know why I'm saying 2 and 3. 3 and 4. This column becomes the first row, like that. The next column, which is negative 9 and 2, becomes the second row. This column becomes the third row, like that. So if you look at, let's take note of the rows. We have 3, negative 9, 0. It becomes the first column here, which is 3, negative 9, 0. The second row is 4, 2, 1. It becomes the second column, which is 4, 2, 1. So if you transpose, this will exchange. So for this one, it's a 2 by 2, meaning that it just remain as a 2 by 2. So this is how we transpose the matrix. The columns become the rows, and the rows become the columns. Let's just answer a few questions on how to deal with rows and columns. Okay, so given that matrix A and matrix B, so it's important to note that matrix A is a 2 by 3. That's the order. This matrix is a 3 by 2. Okay, find the exact value of this here. So we can only add and subtract matrices if they have the same order. That's why we haven't been given a question to say what is A plus B, because the order is not the same. But otherwise, we're going to transpose them. So for A, we have 2A minus B transpose. So this number here, the 2 is just a scalar. So 2 multiplied by matrix A is 3, 4, 0, negative 1, 2, 4, minus B transpose. So this is our B. Let's transpose it. So transposing B, the rows become the columns become the rows. So the first column is 117. 117 is the first column, so it becomes the first row, 117. The second column is 0, negative 2, 3, so it becomes the second row, 0, negative 2, 3. Okay, then from there now, what we're going to do is this. We have a scalar there, meaning that this scalar must multiply everything inside the matrix, so that we get 2 times 3, we have 6, 2 times 4 there, we have 8, 2 times 0 is 0, 2 times negative 1 is negative 2, 2 times 2, we have a 4, 2 times 4, we have 8 again. So minus this matrix, so this matrix has no scalar, so we'll leave it as it is, which is 1, 1, 7, negative 2, and 3, like that. Okay, so now let's subtract the two matrices. So 6 minus 1, we get 5. 8 minus 1, we get 7. 0 minus 7, we get negative 7. Negative 2 minus 0, we get negative 2. 4 minus negative 2, we get a positive 6. 8 minus 3, we get 5. So this is the value of that expression that we have there. Okay, let's find the next one. So the next one is A transpose plus B. So now we have to transpose matrix A, and then we add it to B. So this is our A, so let's transpose it. So transposing A, the first row becomes the first column. So the first row is 3, 4, 0. So it becomes the first column here, which is 3, 4, 0. The next row is negative 1, 2, 4. So negative 1, 2, 4. What we've done here from this to this is we've transposed, because here we've been told to say find A transpose, add it to matrix B. So that is A transpose. So if you add it to matrix B, which is this one here, what we're going to have will be 1, 1, 7, 0, negative 2, 3, like that. That's what we get. Now let's just simply add these two matrices. So adding these matrices now, 3 plus 1, we get a 4. Negative 1 plus 0 is negative 1. 4 plus 1 is 5. 2 plus negative 2 is 0. 0 plus 7 is 7. 4 plus 3, of course, is 7. So that's what we get. So this is how we use transpose matrix to add and subtract matrices. I hope you understand the concept of the transpose. Just to summarize it, we said that the rows become the columns and the columns become the rows. Also, we mentioned that if a matrix has 2 rows and 3 columns, then the transpose will have 3 rows and 2 columns, just the opposite. So what is an identity matrix? So now let's look at identity matrix. So an identity matrix is simply a matrix which has ones in the principal diagonals or the major diagonal, then it has zeros everywhere. So like we have here, it has ones there, it has ones there, it has ones there, and everywhere else it has zeros. Now it's important to note that an identity matrix is always a square matrix. A square matrix is simply a matrix which has a same number of columns and rows. So the order of an identity matrix will be either 2 by 2, 3 by 3, 4 by 4, just like that. So what are some of the properties of an identity matrix? Well, an identity matrix is used to find sometimes the inverse, sometimes it's used to find so many things, even as well as orthogonal matrices. But one property you should know about an identity matrix is that an identity matrix is more like the number one. We know that the number one multiplied by any other number, what we'll get will be the same particular number. Meaning that if you get an identity matrix, you multiply it with any other matrix, the result that you get is that particular matrix, like we saw in multiplication. So, given matrix A, if matrix A is maybe a 3 by 3, then you multiply it with an identity, this one here, the result that you get will simply be matrix A. So that's one unique property about an identity matrix. Then one other thing to note about an identity matrix is that an identity matrix is idempotent. So to understand what an idempotent is, I'll look at it in this very video. So we'll be looking at matrix multiplication. We'll look at how to multiply two or more matrices and the rules that are required to be followed. Okay, so let's go step by step. So firstly, you cannot multiply two matrices if they have the same order. Remember what we talked about in order of the matrix is either 2 by 3, 3 by 2, just like that. That is the rows and the columns. Then when multiplying two matrices, for example, A and B, that is A times B, you have to make sure that the number of columns of the first matrix, which is A, has the same number of rows in the second matrix, which is B in this case. So what I want to look at is making sure that the first matrix, the column is the same as the number of rows in the second matrix. You understand that once we start looking at some examples. So what we're talking about here is, for example, if you have A, matrix A has the order 2 by 3. Matrix B can have the order maybe 3 by 4, such that the number of rows, so the number of columns in A is equal to the number of rows in B. That's what we're saying. Okay, so the remaining numbers that you have, which is 2 and 4, will give you the matrix of the product that you're looking for. So yeah, the product of the two matrices. Then lastly, we're saying that matrix multiplication is always done. This is very important, very important. It's always row by column. So let's just quickly look at some examples. Then there's something that we need to talk about as well. That is the identity matrix, of which we'll talk about as the last example. So make sure to watch the video until the end. So when multiplying matrices, it's very important to know the order of the matrices that you're multiplying. So order, we simply mean the number of rows and the number of columns. So how many rows do we have in this? We have 1, 2, 3. So this is a 3 by 2, like that. How about the next matrix, which is this one? It has 2 rows, 2 columns. So that's a 2 by 2. So the idea is that, like we said, the columns, this number here and this number here must be the same, meaning that our final answer must be a 3 by 2. The remaining numbers, which is a 3 by 2. So let's go ahead and multiply our matrices. So let's produce a 3 by 2. So multiplying these matrices, this is what will happen. We're going to multiply rows times the column. So the first row times the first column. So 3 times negative 2, we get negative 6. So we add negative 1 times this 3 here, we get negative 3. So the first row times the first column. So now we're going to move on to the next row. So the next row, so this is a continuous process, of course. You just multiply row by column, row by column. So now this row times the first column, same thing. So 7 times -2 is -14. 2 times 3 is 6. We're adding all these values here like that. Again, row by column. Third row, first column. So 2 by 2, we'll get -4. 5 by 3, we're going to get 15. So we are done utilizing this first column. So now each row is going to multiply the second column. That is 3 times 0, we get a 0, plus -1 times 4, we get -4. Then 3 times, sorry, we start with 7. 7 times 0, we get a 0. 2 times 4, we get 8. 2 times 0, we get a 0. 2 times 5 times 4, we get 20. The idea is, like we said, row by column. So adding these two numbers, we'll get -9. Adding these two, we'll get -4. Adding here, we get -8. Adding down there, we get +11. There we have 8. There we have 20. Now, if you are paying attention, you are going to see that in this answer that we have, the order of this matrix is a 3 by 2 because it has 3 rows, 1, 2, 3, and 2 columns, 1, 2. That's why I said these remaining numbers will tell you the order that you must have in your final expression. Okay, let's look at the next matrix. As usual, before anything, it's important to know the order of the matrices. So the order of this matrix is a 3 by 1. And the order of this matrix is a 1 by 2. So 3 by 1 because it has 1, 2, 3 rows and 1 column. This one has 1 row and 2 columns. So since these two numbers are the same, what we're saying is that our final answer must be 3 by 2. So let's see how we can produce a 3 by 2. Okay, let's start. Again, row by column. So first row times first column. 3 times 2, that is 6. So we just have 1 row here. Or rather, we just have 1 column. So 6 times 2, there we get a 12. 1 times 2, we get a 2. 3 times -5, we get -15. 6 times -5, we get -30. 1 times -5, we get -5. That's it. That's our answer. So now, again, same thing. Our answer is a 3 by 2. Because there we have a 3, there we have a 2. Okay, so for this next one, let me try to do it very slowly so that you can be able to follow through. The idea is, number 1, knowing how many columns and how many rows you have. So for this one, it has 2 rows and 2 columns. 1, 2 rows, 1, 2 columns. For this matrix, it has 2 rows, 1, 2. And how many columns? 1, 2, 3, 4. Like that. Now, since these two numbers are the same, it means that our final answer must be 2 by 4. So let's produce a 2 by 4. So this is what will happen. I want to produce a 2 by 4. Row by column. So each row multiplies each column. So the first row here is 2, 4. Multiplies 1, 0. So 2 times 1, that is 2, of course. 4 times 0. So we're going to add here. 4 times 0, we're going to get a 0. Again, same thing, row by column. So this row now multiplies this column. 2 times 3, we get a 6. Plus 4 times -1, we get -4. Same thing, row by column. So this row multiplies this column. 2 times 4, that is 8. 4 times 7, that is 28. Again, same thing, row by column. 2 times 1, that is 2. 4 times 0, that is a 0, like that. So we are done with the first row. Now let's go to the next row. So we're using this row now. Row times column, row times column, row times column, row times column, just like that. -1 times 1 is -1. 5 and 0 will give us a 0, like that. -1 times 3 is -3. 5 and -1 will give us -5. -1 times 4 is -4. 5 times 7 will give us 35. -1 times 1 is -1. And 5 times that 0 that we have there, we just get 0, like that. Then it's just a matter of now adding everything that we have. So there we get a 2. Down there we get a negative 1. Here we get a positive 2. Here we get negative 8. Here we get, should be 36. There we should get a 2. Down here we should get 31. And there we should get negative 1. Like that. So if you're paying attention to what we're doing, we can say that this is a 2 by 4. There are 2 rows and 4 columns, which is what we have from these 2 remaining numbers. Okay, now let's look at this big one. So we're going to apply the same concept. It's always row times the columns. So let's state the order. This is a 3 by 3 and this is a 3 by 2. So since these 2 numbers are the same, then we can multiply these matrices. So now you might have a question to say, what if they're not the same? If they're not the same, then you can't multiply the matrices. Just like we looked at addition, if 2 matrices don't have the same order, then we can't add them. Same with multiplication. If this rule is not satisfied, we cannot multiply them. Okay. So we can clearly see that our final answer must be 3 by 2. So let's see how we produce that 3 by 2. Each row will multiply each column. So let's start. 4 times 6, we'll get a 24. 3 times negative 2, we'll get negative 6. 7 times 0, we just get a 0, like that. Again, the same row times the next column. So 4 times 3, we get a 12. 3 times 1, we get a 3. 7 times negative 3, we get 21. So go to the next row times the first column. Negative 5 times 6, we get negative 30. 0 times negative 2, that's just a 0. 2 times 0, again that's another 0. So negative 5 times 3, we get negative 15. 0 times 1, we get a 0. 2 times negative 3, we get negative 6. We go to the last row times each column. 1 times 6 is 6. 1 times negative 2 is negative 2. 1 times 0 is 0. 1 times 3 is 3. 1 times 1 is 1. Negative 1 times negative 3 is a positive 3. Okay, then from there, let's just add the corresponding values. 24 minus 6, that will give us 18. 30 plus 0 plus 0 will just remain negative 30, as it is. 6 minus 2, that's a 4. This will give us 15. 15 minus 21 will give us negative 6. Then if we add these 2, we're going to get a negative 21. If we add these 3, we're going to get a 7. So now remember, the remaining values was a 3 and a 2, and this matrix, of course, is a 3 by 2. Okay, now let's look at the identity being used, how to use the identity and what the identity is. Given that matrix A is this one here, and matrix B is that one, find the value of A squared. So if you've been taught to find the value of A squared, then what we're saying is that the matrix A is multiplying by itself. Do not square every value in A, just multiply matrix A by itself. So A squared, this A squared that we have here, is the same as matrix A, which is 4, 2, negative 3, 1, multiplied by itself, 2 and 1. Okay, so since we're multiplying a 2 by 2 and a 2 by 2, then of course our final answer will also be a 2 by 2. So 4 times 4, we get a 4. 3 times negative 2, we get a 6, like that. 4 times negative 3, we get negative 12. Negative 3 times 1, we get negative 3. 2 times 4, we get 8. 1 times 2, we get a 2. 2 times negative 3, we get negative 6. 1 times 1, we get a 1. So let's just add up everything. So adding up everything, what we're going to get is negative 2, negative 15, positive 10, and negative 5. So this is the value of A squared. Okay, now let's look at matrix B. Matrix B says A multiplied by I2. I subscript 2. So this I represents the identity matrix. An identity matrix for example I2, is first of all a square matrix. It has same rows, same columns, whereby the major diagonal, you have ones in the major diagonal and zeros everywhere. So if we're talking about I3, what we're saying is that we have 1, 1, 1 and zeros throughout, meaning that it's only the major diagonal which is going to have ones. So I4, just the same concept. So now to find the value of A times I2, this is as good as saying matrix A, which is 4, 2, negative 3, 1, multiplied by the identity, which is 1, 0, 0, 1. So multiplying any matrix by the identity gives you the same matrix. So we see that what we're going to get is simply this matrix again. So 4 times 1, that will give us a 4. 3 times 0, that will give us 0. 4 times 0, we get a 0. Negative 3 times 1, we get negative 3. 2 times 1, we get a 2. 1 times 0, we get a 0. 2 times 0, we get 0. 1 times 1, we get a 1. So adding these numbers, we get 4, negative 3, 2, and 1, which is the same matrix A. Meaning that when any matrix, for example A, is multiplied by an identity, what you're getting is just the same matrix, which is matrix A. Let's look at the product of AB. That is question C. So the product of AB, we start with A, which is 4, 2, negative 3, 1, multiplied by B, which is 1, negative 1, 2, 3, negative 4, 0. So first of all, we need to know the order of these matrices. For the first one, of course, is a 2 by 2. Then this one is a 2 by 3. So since these two values are the same, then our final answer must be a 2 by 3. So let's see how that comes out. So row by column. So the first row times the first column. 4 times 1, that is 4. Negative 3 times negative 1, that's a positive 3. Again, 4 times 2, that is 8. Negative 3 times 3, that's negative 9. 4 times negative 4, that's negative 16. Negative 3 times 0, that's a 0. 2 times 1, that is a 2. 1 times negative 1, that's negative 1. 2 times 2, that is 4. Negative 1 times 3, that will give us 3. 2 times negative 4 is negative 8. Then 1 times 0, of course, is just 0. So adding these values, what we're going to get will be 7 there. There we'll have negative 1. Here we'll have negative 16. Here what we're going to get is simply 1. Then here we have 7. Then the last part have negative 8. Like that. So of course we can see that the order of this matrix has 2 columns, 2 rows, and 3 columns, just like we said from the beginning. So that's it. This is how we multiply matrices. To conclude this video, let's look at idempotent matrices. So an idempotent matrix, first of all, is a square matrix, which has same rows, same columns, that remains unchanged when multiplied by itself. So given a matrix A, if you multiply A by itself, that is A squared, and the result you get is still the same A, then that matrix is said to be idempotent. So let's try that. We have matrix A here. Now let's find the result of A squared. So A squared will be given by 412 minus 1 minus 3, multiplied by itself, which is 412 minus 1 minus 3. So row by column, this row times this column. So 4 by 4, we get 16. Negative 1 times 12, we'll have minus 12. 4 times negative 1, we'll have minus 4. Then negative 1 times 3, we'll have a positive 3. 12 times 4 should get, is it right? Yeah, this times this. So 12 times 4 should get 48. Then 3 times 12, we should get minus 36. 12 times negative 1 is minus 12. And lastly, 3 times 3 will have a positive 9. Okay, so what does this result to? This gives us 4, 12 here. Here we have -1. Here we have -3. So you can see that the result that we're getting is the same matrix A multiplied by itself. This concludes that this matrix is idempotent. Now, remember, we're talking about matrices which are square matrices. This time around, we have a 3 by 3. Let's see how we can prove that this matrix is idempotent. So again, just the same thing. We are going to multiply it by itself. Then if we get the same result, then we can conclude that it's indeed idempotent. So let's find the matrix B squared. So B squared will be given by 2 minus 1, 1 here, minus 2, 3 minus 2, minus 4, 4 minus 3, multiplied by itself. Hence we get 2 minus 1, 1, negative 2, 3, negative 2, minus 4, 4, minus 3. So row by column. So this row times this column, just like that. Okay. So 2 times 2, that is 4. Negative 2 times negative 1, that is a positive 2. Negative 4 times 1, that is minus 4. Then again, 2 times negative 2, minus 4. This and this will have a minus 6. This and this will have a positive 8. Okay. Then 2 times negative 4 will have minus 8. Negative 2 times 4 should have another minus 8. Lastly, this times that will have a positive 12. Okay. We're done with the first row. Let's go to the next row. So negative 1 times 2 will have negative 2. 3 times negative 1 will have minus 3. 4 times 1 will have a positive 4. Negative 1 times 2 will have a positive 2. 3 times 3 will have a 9. 4 times negative 2 will have minus 8. Negative 1 times 4 will have a positive 4. 3 times 4, that is a 12. 4 times 3, that's a minus 12. Okay. So third row, 1 times 2, we'll get a 2. Here we'll have a positive 2 again. Then lastly, we'll have a minus 3. Here we'll have negative 2. Here we're going to have a minus 6. Then here we'll have a positive 6. Lastly, here what we have? We have 1 times negative 4, that's minus 4. Negative 2 times 8, minus 8. And lastly, negative 3, positive 9. Okay, so what's the result for B squared? Here, we get a 2. Remember the 4s will cancel, we get a 2. Here, we get a minus 1. Then down here, we're going to get a positive 1. Here we have negative 10 plus 8, which is minus 2. This is 9 minus 8 is 1 plus 2, that's a 3. The 6 will cancel, negative 2. So negative 16 plus 12, negative 4. The 12 will cancel, positive 4. Then here we can see that we'll have a minus 3. So we can see that B squared is the same as B, and you can conclude that this matrix is indeed idempotent. So one last example before we conclude. Given that matrix A is idempotent, find the value of x if matrix A is given by this 2 by 2 matrix. So to start with, you need to know that an idempotent matrix is a matrix such that when multiplied by itself, it gives the same matrix. So meaning that A squared is equals to A. That's a property of an idempotent matrix. So with that in mind, let's find the value of A squared. So A squared will be given by the matrix multiplied by itself. So minus 6 here of x multiplied by 3, 1, minus 6 here of x. So A squared will be equals to 3 times 3, that's 9. 6, negative 6 times 1, that's minus 6. 3 times 6, that's minus 18. Negative 6 times x, that's minus 6x. 1 times 3, that's a 3. X times 1 should get x. 1 times negative 6 is minus 6. X times x, we have x squared. Okay, so because of this property, we can say x squared, what we have? We have the 3. Here we have 3 plus x. There we have minus 18 minus 6x. And down here we have minus 6 plus x squared. So this is the matrix A squared. Now remember, because of the property of idempotent, this is equals to matrix A, which is 3, 1, minus 6, x, like that. Okay, so now, since these two matrices should be the same, what we can easily do here is, we can say the 3 is equals to the 3, that's fine, meaning that this part is equals to negative 6. So minus 18 minus 6x is equals to minus 6. So negative 6x is equals to negative 6 plus 18, meaning that negative 6x is equals to positive 12. Hence, the value of x is simply minus 2. If you don't like that part, you can use the other part as well. You're not restricted to one. You can say this whole thing is equals to 1. So you can say 3 plus x is equals to 1. So x is equals to 1 minus 3. So x is equals to negative 3. Okay, so we'll get the same result. So even this part here, you can equate it to x, but you have a quadratic equation. You have two values when you solve that quadratic equation. But just know that one of those values is the accurate one, which is a negative 2. So there we have it. That concludes our first session of this series. I'll see you in the next one. Thank you very much.